actually start, Dr. Ali. So, yep, again, we would like to welcome everyone who have attended to this, who attended in this webinar today. Okay, so we can actually see numbers, which is great. And then, yep, just a reminder for those who are, for you to be able to have a laser focused attention to this webinar. I would like to request everyone to please disable your notification or your sounds from your end so you can actually see the instructions on your screens. Okay. And then at the same time, if you do have any questions for Dr. Ali about the topic, please feel free to post it up in the Q&A section on the under the Q&A section or function at the top of and right corners of your screens. Okay, so you can actually see that on the top. Okay, and then for common questions and FAQs, this is where most of the questions that I received during the webinar. So everyone who have registered will actually receive a copy of your slides, a copy of the slides, and of course a video recording. And this will be sent to, we will try our best to send this to you within the 2 business days. Okay, so just kindly monitor your junk mails as well or spam messages because it usually goes straight there. So kindly check on that one. And of course, since this is a technical topic webinar, we will be issuing a certificate of attendance for those who have registered and who have completed the webinar. So stay tuned until the end of this webinar because instructions on how to claim your certificate of attendance will be provided to you. Okay. So yeah, about EIT. So for those who have, just newly attended one of our webinars or just attended to this webinar, EIT is actually an education provider based in Perth, Western Australia. We also have a campus in Melbourne, and at the same time, we recently opened our Brisbane campus. Okay, so we specialized in engineering courses. We offer professional certificate courses, advanced diplomas, graduate certificates, graduate diplomas, sorry, bachelor's, master's and doctor of engineering courses. So these programs are actually industry-oriented programs which are developed and of course valuable to employers. And then some of our programs are accredited by the Australian government, and at the same time with engineering accords such as Dublin, Sydney, and Washington. So these particular courses are being delivered by industry experts and lecturers like Dr. Ali here, and of course being delivered through a unique delivery model such as live webinars and state-of-the-art hands-on workshops and remote laboratories and simulation softwares. Okay, so for today's topic, that would be unlocking the power of edge computing, real-time decision making at the device level. So this will be presented to us by Dr. Ali Marzougi. Correct me if I pronounce it right, Dr. Marzougi, right?
Great.
So yeah, he's been our EIT lecturer. So I will allow Dr. Ali to introduce himself further, and then we can proceed with the presentation. Okay. So, Dr. Ali, would you mind sharing some information about you to our audience today? Thank you so much.
Thank you so much, Marvin. Thank you so much, everyone, for attending to this webinar presentation. I know that some of you sacrificed your time. Maybe this is the middle of the night or something. So I shortened my speech in case of introducing myself to be able to talk more about edge computing. So my name is Ali Marzouri, and I have about 20 years experience. So you can read it while you get the slides back. So mainly I started my occupation at about 2000 as an instrumentation engineer and electrical instrumentation and electrical engineer in oil and gas field, and then the working too much in industry. Then I've been promoted to become supply manager in the same field, and then I moved to Malaysia and Singapore, worked there in not oil and gas industry, but the other industries. And then I moved to Australia, pursuing my PhD at the University of New South Wales. Then since 2019, I was working with EIT, which is my absolute pleasure. So at the same time, I'm working in industry as a service manager in Australia. So this is a brief introduction about myself. The rest you can find it either in the lecture slide or through the Google search. So it's
Yeah, and the
for
website
everyone.
as well. They can
Yeah.
also check us
And the
out on the
website as
website.
well. Yeah, yes, in
Yes,
EIT
yes,
website. Yes.
exactly. You can take control of the slides, Dr. Ali. Thank you.
Thank you so much. So let's start with the agenda. So in this webinar, we introduce computing, and step by step we go forward to reach the edge computing and the importance of edge computing and the advantages. And we finalize the webinar by case study. Actually, the other plan is to provide um, a practical webinar probably in later, so you've been notified by Marvin later on. So in the other webinar, which is the continuous of this webinar, we try to show you how edge computing works experimentally by um, sensors and devices. But in this webinar, we are going through the introduction, introducing the edge computing, where edge computing comes from, and why edge computing is necessary in um, industry. So first of all, we start with the computing concept. Computing concept is not something that I want to go through deep down because it's something which you are using daily. So we must use computers because actually our life is dependent on the computer. They are efficient for calculation, for computation, but for your information, it comes from Latin word computation, which means reckoning or calculation. So computing is enhancing the reckoning and the calculation, and now on the decision making and the base of robotics and everything. So it impacts on different levels of industries, including the business, finance, industrial applications such as autonomous um, cars, autonomous vehicles, and automatic control of the systems in healthcare, education, government, home, entertainment, law, and agriculture, and so on. And it's ongoing process. So it's developing every day by AI and some other features of computing. So if we want to start historically about the computing development, first of all, imagine that there was a simple computer with a CPU and main processor, and then people found it challenging to work with only one computer. So they must be expanded. So this expansion started with parallel computing. So we define a parallel computing as using multiple cores, multiple CPUs, which are working separately, but they share their data, their analyzed data, their processed data um, with the main memory. So they share all the information in the main memory, and the main memory starts doing further action on the processed data. And then it continued with distributed computing. So distributed computing is a develop of parallel computing, which is currently used in industry in our daily life. Say, for example, you have multiple computers. distributed in different location. Actually, they are segregated geographically in different locations, and they provide you. Each of them provides some tasks. Each of them doing some tasks, and then these tasks will be combined over a network for further action. What is the benefit of distributed computing? The benefit of distributed computing is increasing or enhancing scalability and fault tolerance. For example, uh, an example is cryptocurrency mining, which everyone can mine if we can bear the um, um, electricity costs actually with a simple computer at home or few computers, and then share this information over the network or online collaboration platforms and so on. Then it continues with cluster computing. Cluster computing is um, another development of computing systems. What you can see in this image is the Oak Ridge National Laboratory in Australia, which includes 200, which includes supercomputers, each of them 200 petaflops. Um, um, Storage, so it means that they can handle 200 quadrillion floating point operator. So for some of you who doesn't have any idea about quadrillion, I have to say that quadrillion means one with 15 zeros. 15 zeros in front multiplies 200. So what is the advantage of this cluster computing? The high performance um, uh, task job doing. So they can balance the loads over the multiple servers, web servers. So if if some failure happens in one of the servers, the other keeps continue working, and they are using for very complex tasks such as weather forecast. Um, or for scientific simulation. So any scientific complex modeling system. Then we have another computing model, which we call it as utility computing. Some of you may use utility computing. This is the on-demand computing resources, so you can uh, hire or borrow or subscribe for one of them, and then they are normally cloud hosting services. So you hire for a period or for a lifelong or whatever time you need it, without being nervous about how to maintain, how to pay for the power bills, or so on. The only thing is you have to pay a few amounts to borrow this platform and use your daily tasks. So it could be your business, it could be your industrial tasks or student tasks, or so on. So in this case, we can say that we have different servers such as AWS, for example, Amazon Web Services, such as MQTT or Hive MQ, which are the platform, or Node-RED. Node-RED is a platform that provides you opportunity to be able to connect your actual device to the cloud and visualize data has been gathered by the sensor. So we call it as utility computing, and then we go to grid computing. Grid computing is expansion of utility computing. So you have a grid, you have multiple grid nodes which are connected, but each of them individually does the job done. So we have multiple platforms for that. For example, you have Java client, you have .NET client, you have C++ client, and so on. So each of them can be hired based on your capability, and you can use the devices or use the platform for your normally we call this model as or this grid computing system as um, um, uh, computing system which is useful for heterogeneous. So if I want to give you an example of this, there is a very interesting example which we call it as SETI at home project. So SETI as at home project is a project. It's a global project. Everyone can interact in this project. So you are using your personal computer connected to the server, and then you can record signals that uh, possible signals that has been received from the space for searching or investigating if there is any extra terrestrial signals comes from, and then all these data help um, the human body to understand if there is any extraterrestrial signals in the space or not. So we distributed as the grid to help our science development or information development, and everyone can attend to this. This is a main example of grid computing. So imagine that if we want to use only one server and one platform to get these data. So what is the difference? What is the comparison between the power consumption and so on? We have another model for computing, which we call it as cloud computing. So we slowly getting closer to the main purpose of this webinar. So cloud computing is an on-demand services. When we are going through the definition of cloud computing, which is delivering of computing services, for example, data would be gathered and stored in a cloud base, and people can hire some part of these cloud-based servers and use their own tasks. You may say that, all right, so what is the difference between cloud computing and cluster computing then, or the other, or grid computing? What I'm saying is there is only slight difference between each of them, and the difference is cloud computing is a cloud that covers all of the previous concepts that we talked about that. So all of them will be covered in a cloud. So cloud computing has the features of all of the previously explained models. What you can see here is a pyramid that explains the cloud computing. For example, we have the lowest level as IaaS, which AWS or Amazon Web Services is the most famous example of this level. So in this level, you have limited access, limited opportunity to do some tasks. So you get the basic web space, and then you can do some sort of simple tasks. Then one level up is a PaaS. So IaaS stands for infrastructure as a service. So this gives you an infrastructure, a basic infrastructure for services. We have PaaS, which is a platform as a service. So it gives you a platform as a service. Therefore, you have opportunity to do more tasks. So you have some um, further opportunities. And then we have SaaS, which is the top of the pyramid. So it's a software as a service. So you have full access to full capacity of the services. So this pyramid explains the cloud computing in a short time in more detail. Then in cloud computing, we have a concept that we call it as um, ubiquitous computing. So we want to talk about the emerging paradigm of ubiquitous computing. What you can see in the image number 4, in the image reference 4 actually, is the osmotic computing, which is one type of this paradigm. So ubiquitous computing. So we have multiple or three main different forms: jungle computing, fog computing, and osmotic computing. So I explain each of them a little bit in detail. In case of the cloud computing, before I'm going further in details with jungle computing and osmotic computing and fog computing, I have to explain something to you. What you can see is a scenario based, which is comparing cloud computing and edge computing. I've not talked about edge computing yet. I understand, but I've already talked about cloud computing. And this image shows you why we we needed to jump over cloud computing to edge computing. Look at the image carefully. You will see that in cloud computing, you have a server, which is a centralized server, including all necessary components such as database and so on. And then all the devices are communicating with these clouds. First thing that comes to your mind is the latency. And the second thing that comes to your mind is the power consumption, right? And I have to say that the third thing that comes to your mind is challenge of failure in the device. So these all challenges plus a lot more results in edge computing, which we are talking about that later on. But why did I explain these? Because I wanted to summarize all of them in one main important issue, which is high bandwidth. So while we are using traditional cloud computing without applying edge computing, the bandwidth has been occupied by cloud computing is very high. So we needed to be sectionized, to be smaller and smaller, to be able to have better control. All right. So back to the explanation of jungle computing, fog computing, and osmotic computing. In case of definition of jungle computing, we can say that imagine that you are walking down in a jungle. So what you can see different type of bushes, different types of trees, different types of animals, and so on. So jungle computing gets its concept from that definition of jungle. So you can see different components, different systems in general in one system, in one whole system. So you can see you can you can see actually combining of various computing paradigms that we've already talked about that. So say for example grid, say for example cluster computing, say for example cloud and supercomputers. Um, so all of them combined in one system that we call it as a jungle platform or a jungle computing. So what is the application of jungle computing? The application of jungle computing is to be able to simultaneously do the very complex task. So each of these paradigm actually does their own job, and then they've been combined all the data, all the results for further or for final result or further investigation or further study. For example, for simulation purposes, in large scale simulation purposes, for example, for grid computation, for power production, and so on. So it increased the flexibility, decreased the power consumption, and the latency. We have another model which we call it as fog computing. So what is the fog computing? Fog computing is extended model of cloud computing. So imagine you have fog, imagine you have cloud, and then you have fog. So this is the extended version of a cloud. So when we say extended version of a cloud computing, it means that we have multiple computation as well. So we have storage as well. We have networks, different layers of networks as well. So we have data resources. Um, so we have different multiple types of devices, and these method also help to decreasing the latency and increasing the efficiency. For example, traffic control, traffic light control, or processing the traffic light data, which has been gathered by the smart traffic controls. So it optimizes the performance of traffic lights. We have osmotic computation. In osmotic computation, we are facing with dynamically distributed workloads between the cloud and edge. So what we can see is osmotic is a layer in between cloud and edge of uh, the problem, edge of the cloud, right? So or edge of the environment. So it again it optimizes the performance and scalability. And as an example of osmotic, for your information, we have wearable devices on healthcare. Recently, currently, if you have, if you see any patient with struggles with sleep apnea or the heart condition problem, heartbeat rate problem, or lot other disease or issues. So they have some devices attached to them. Either they can wear these devices, or they can put the devices next to them, or attach to the body and do the daily based job. So they can do exercise, they can sleep with that, they can run, work, and so on. And data will be transferred automatically to the server. So this is an example of osmotic computation. So now we are going to dive a little bit deeper to challenges with cloud computing. As I mentioned previously, latency in real-time application, the network, the bandwidth, network traffic, the cost of transmission, the power consumption, all of them could be, and scalability, which is very important, all of them could be considered as the challenges in cloud computing. That's why we developed edge computing, and edge computing solve many of these problems or optimize the problems, the issues that we struggle with by bringing the components from the cloud to the edge of the cloud. So if we have cloud like these, includes all the devices. In cloud computing, we have all the devices, for example, in a main server in the cloud, in one country, the server in one country, and it's been gathered data from another country. But while we are talking about edge computing, these devices will be distributed on the edge of the cloud so they can gather these data easier in decentralized form. And then they have opportunity to transfer these data over the network, the main server for the storage, for monitoring, for further investigation, and so on. So what we can see, optimizing the storage, optimizing the latency, optimizing the power consumption, um, scalability, because the sensors, actuators, and so on comes to the edge of the network in the location which is geographically different with the main service location or cloud location. Therefore, they can be scalable, right? And they have capability of taking action or making decision immediately as required. And then they can send data to the server. Another important um, interest for edge computing is if a failure happens, which we are talking about that um, a little bit later. But before I'm going through the advantages of edge computing, let me talk about the evolution of edge computing. So edge computing concept started from 1998 by development of content delivery network or CDNs. If you are familiar with Netflix, which I believe that most of you are familiar. So in Netflix streaming, video streaming, previously it was something like a server located in, for example, say in the United States, and Netflix must provided their services in Australia. So now, since 1998, this concept happened. And that was an example, anyways, for you to for better understanding. So they brought all these features near the local server, right? And then the video stream would be analyzed, would be processed, and then transfer between the source and destination and vice versa, right? So it keeps continue in a slow pace uh, by 2005 by developing the function catching for mailbox management, for example. What does it mean? It means that you are going to your mailbox and then you can sort out all unread mails or sort them based on date and so on. So it's established that 2005, and then so locally you could do something with your emails, and then at 2009, the cloudlets have been introduced, which was a small scale decent data center located in, located closer to the consumer, right? For example, augmented reality. So in augmented reality, you have this opportunity to use cloud-based. Then we have fast pace for development or evolution of edge computing since 2010 up to 2013. We had mobile edge computing, so MECs, which are developing or which are development of the autonomous vehicles sensors and autonomous vehicles um, um, devices. For example, we have LiDAR in autonomous vehicles. We had camera feeds in autonomous vehicles for image processing and proximity finding and doing some tasks such as braking and so on, all right, automatic tasks. Then it keeps continuing at 2012. Cisco introduced a fog computing, which was the extended version of cloud computing. And then 2013, edge computing concept has been formalized and it's been stabilized at 2015 to 2018. It means that all the standards and definition officially have had been placed, right? So for example, it's been used for automating deployment, scaling, and management of centralized applications, such as, say, for example, using authentication um, um, for payment processing. Normally, we are using authentication when nowadays, currently, you may use authentication in your mobile phone for logging to your EIT's, I don't know, uh, um, web, email or cloud or whatever. All right. So, or not just EIT, anything else as well in your workplace, in your educational institution, and so. So these are edge computing because everything has been kept closer to the edge of the cloud. It means that they are closer to you as consumers. And as an example, Kubernetes. So Kubernetes is the platform that I gave you an example for that just right now. So we have advantages of edge computing. Um, so as I mentioned previously, it can increase the efficiency of task operation and definitely reduces the latency and network bandwidth. So optimizes the network bandwidth usage. It lowers the communication and storage costs because you have local storage and you have capability of communication real time in the local area and then with the main server or with the cloud. While you have segmentized edges, then you have a smaller component, a smaller, say, platforms that working with the devices. Therefore, providing the security for them, which is very important, which is one of the most challenges of today's or of current industries, especially for such kind of critical industries such as banks, such as um, home affairs and so on, which are dealing with the very um, specific information of the people um, or confidential information of the people. So it gives the opportunity to be able to provide a higher level of security. So cyber security, providing cyber security for the devices is way easier. And then consequently, while you have higher secure system, then the reliability of the system increases, improve data privacy, resilience during the network failure, which is very important. If something happens to the network, it doesn't mean that your system is not working at all because you have local server, you have local system, and this local system has its own storage. However, this storage is not that huge, but it can store data, it can make decision immediately, it can get the job done um, real time while it's required before um, um, before getting or transferring some information to the main server or cloud. So if there is some failure happens to the system, to the network, then the local device keeps controlling the system, keeps working until the failure will be cleared, and then it communicates or transfers data which is required. If something happened to any node, if something happened to any local servers, then again the whole system are working. It doesn't impact on the whole system, so it increase the reliability or resilience during any network failures. It gives you a scalable and governance and enhances cloud scalability for offloading the data. So the end of the spectrum, while we have edge computing, it means that we have better data quality, which are more usable for us. So what you can see in the image is a future trend in edge computing. Uh, Edge computing, similar to the other computing paradigms, such as cloud computing, such as fog computing, such as cluster computing, or so on, um, is improving. And definitely, the next level is developing something else. In this stage, we are using edge computing in some technologies such as digital twin, we are using in manufacturing and establishing the factories, smart factories. So this digital twin is a platform that, or a software that gives you opportunity to simulate in a real base form a factory, for example, that you want to establish. So you can see everything, you can get the bugs and all the, you can predict all the failures happen before it's been established. So you can see the harvest. So this is system simulation and modeling. Or in autonomous systems or in IoT devices, nowadays you can see that in many countries, the houses, the homes, the units, apartments, and so on, they are tending to become more smart and smart. So we have smart homes, IoT-based homes with smart devices. Or factories. We have the concept of smart factories. They are using more robots in case of the operation. They can communicate, they can make decisions in some special cases. And 5G and 6G and so on. So we are not going through in details. And we are going to talking about the architecture, introducing the architecture of edge computing. When we are talking about the edge computing, this is important to know what is the architecture of edge computing. As you can see here, edge computing has multiple layers, which we call it as perception layer, we call it as edge computing layer and application layer. So um, what I want to do is I'm going a little bit deep down and explain each layer a little bit deeper. Definitely, we don't have too much time to go deep. um, to the very depth of this definition, but just as an introduction. So what do we have is device layer or perception layer. Device layer or perception layer is defined as the layer includes all IoT-based devices such as sensors, actuators, and electromechanical devices. This is required for data collection, right? So we call it as device layer or perception layer. This is the layer that our edge computing system must understand the needs for the system, right? By how? By collecting data from the devices, the vibration data, the thermal data, the hydraulic data, the electronic, and proximity, and so on. Then we are going a level higher, which is edge layer, or we call it as a processing layer. So this data has been collected by the sensors and transducers in device layer or in perception layer, results in the system understands the concept of the devices, and then it's been transferred to another layer, which we call it as edge layer. So this edge layer is responsible for processing these data for better understanding, right? So this layer locates close to the device. And as an example, we can say that the gateways, the routers, the micro data centers, and so on, and they can handling the process of data analysis, the filtering, data processing, and so on. For example, in edge layer, edge layer. So if we have a gateway, so in the gateway, the video stream will be filtered, and then it's been sent, or summarized data will be sent to the data center or to the cloud, right? Then another layer called as the fog layer. Fog layer is intermediate layer between edge layer and cloud layer. So we have intermediate layer. So let me draw that. We start with device layer. I have latency. And after data gathering, it goes to edge layer, right? Then from there, we have fog layer. Fog layer is intermediate layer. Is an intermediate layer between edge layer. Why we need fog layer? What is the difference between fog layer and edge layer in this case then? There are some data processing tasks which are required more power and they are more complex. So it's not possible to do that to do the task in the edge layer, because in edge layer normally we have limitation of consumption. Therefore, these tasks will be transferred to fog layer, which provides us a better opportunity or a higher power for more complex. And then after this layer, data moves to another layer, which we call it as a cloud layer. Let's call it as cloud layer. So this layer is responsible for aggregating and analyzing data. So it aggregates and analyzes data from the edge nodes worldwide. So you have all the information gathered by the edge devices and transfer to edge layer and fog layers worldwide, and then all transfer to cloud layer for further investigation, for storage, for archiving purposes, for monitoring purposes, for prediction purposes, and so on. So we have these four layers of edge computing that we call it as general architecture of edge computing. And what you can see here is different type of sensors which we are using as a edge sensors or edge devices or IoT devices in different industries. For example, in your mobile phone, there are lots of apps that are working with the camera of the mobile phone. So, camera of the mobile phone could be considered as a sensor, edge sensor. Medical sensors, wearable medical sensors, neural sensors, or which are acting as a brain. So environmental and chemical sensors, radio frequency identification, actuators, and so on. There are multiples of them, hundreds of them. And we have network. And this network has architecture for each system. We have different network architecture, including the network layers and protocols for a system. So some of them has been summarized there. We have Bluetooth, we have Wi-Fi, we have Zigbee LTE, LoRa RFID, Z-Wave spread, and NFC. So each of them has special features in case of the frequency domain, in case of the data rate speed, in case of the range that they can cover, in case of the power usage, in case of the cost. So based on our requirements, we have to find out the best. For example, for long-term evolution or LTE, which we call it as long-term evolution. Sometimes in your mobile phone, you maybe notice that in the network it says LTE. So what does it mean by LTE? This is a 4G system, 4 gigabytes. So and this is a sort of cellular band. So why your network shows LTE? Because the range of LTE is very high, very wide, so it can cover miles, and sometimes you don't have good coverage by your provider. Then, therefore, it's been switched on LTE, so you have more cover. You have more cover. While the speed might be a little bit slower, but it doesn't matter. At least you have coverage. The cost is high. The power usage is medium. If you compare it with Wi-Fi or something like this. So, or you have LoRa or which is long range, or RFID and NFC and so on, which are different protocols. Another concept that we have in edge computing is a layer software that facilitates communication and data processing. It's using for managing data between devices and the edge. So, for example, IoT devices, and you have IoT devices such as sensors, such as transducers or edge devices, sensors and transducers, and um, So this middleware helps to centralize data from these edge devices, multiple decentralized nodes, and share them to um, a centralized environment, which is our cloud. So we have device discovery and management, which has been um, actually which is data aggregation. So we have real-time data processing, which is done by interoperability, and then we have interoperability, which is equal to scalability, and then we have network management in case of the security and privacy, and definitely we have security and privacy of data to be transferred seamlessly to the cloud for integration, and we have data processing and filtering for at the end. So the middleware which normally used in industry are not limited to these four, but they are some sort of famous middleware. We have Hydra, Aura, TinyDB, and Fireware. In general, Hydra and Aura are designed for back-end distributed systems management. So while we have TinyDB, which is a simple database for embedded system, and we have Fireware can work in IoT platform. So for for example, for smart cities or for device data management and so on. And we finalize our webinar with a case study. So in this case study, which is a type of predictive maintenance, companies started to get a problem or issue based on vibration of the system and consequently the failure in the system. They had, so we call it as vibration-based predictive maintenance. The challenge of the challenge that the company were faced with was in traditional model. Um, in traditional maintenance model they had was either they had to do the regular maintenance, which is costly. So, for example, they said doing maintenance every 2 months or every month or every quarter, right? So it's costly because while they dismantled a machine and find nothing, so it was costly and they had to assemble the machine. It's direct impact, as well as the system must be shut down for a while until the maintenance, the regular maintenance, would be done. So it increased the cost, recovery cost, the maintenance cost. And if they didn't do the regular maintenance, they had to wait until a failure happened. So until production downtime, and then they had to repair the machine, which caused definitely a delay in operation, cost furthermore because the device must be dismantled, the equipment must be dismantled, and the failed device must be removed, replaced, and so on. So what they've done, they used edge computing concept. They had enough data for predicting the behavior of the machine. So they used some data, some data collection devices, some sensor on some critical machines which showed the most failure, right? So, for example, in the machine with high spinning rate, um, then these edge devices collect data in real time, every few milliseconds or every few seconds or so on. So while they had some history about these, the whole system, and they gathered these, they collected these data in real time, they could analyze and compare these two and find out that if there is any anomaly in data, if there is any abnormal behavior in the frequency, for example, and if there is, it means that this is a symptom of a future failure of the system, and this is the time for doing a preventive maintenance to make sure that there is no breakdown in the machine, there is no downtime in the machine, and increasing the uptime of the devices. So cost saving, avoiding repair, breakdown, increasing the uptime of the machines, and proactive maintenance are all could be addressed as the benefits of using edge computing in um, this study. So what you can see is some data has been gathered based on the actual case study that we've already talked about that. So they had data gathered as humidity, indoor temperature, heating index, and heat index range. Is what we done, and then based on that, the impact or the effect of each of these changes or variation in data has been provided in effect um, column. So you can see that there is a fatigue, heat cramp, or some other notification or alarm for the system maintenance. All right, ladies and gentlemen, there are few more references that you can refer to for further information. And thank you so much. Appreciate your patience and appreciate your attendance to the webinar.
All right. Thank you so much, Dr. Ali, and of course to our attendees today for being focused on the discussion. So let me just take control of the slides, Doctor. Okay. So for those who have questions about what courses are covered by this topic. So basically, as you can see on your screens, that would be professional certificate course of competency in industrial Internet of Things. We also have the graduate certificate in industrial automation and machine learning. We also have the advanced diploma of industrial data communication, networking, and IT. We also have the online Bachelor of Science in Industrial Automation, and of course the Masters in Industrial Automation. So basically, these are the courses that covers this topic. So if you do have any questions, please feel free to reach us at EIT. Here at course, we at course advisors would be happy to, of course, assist you with that one. All right. So, what are the upcoming webinars? So, as you can see, um, yeah, we do have for the March. Okay, we do have the graduate. I'm sorry. Upcoming courses, not webinars, okay? As you can see on your screens. Apologies for that. And then, yep. So now let's have a quick Q&A session. So basically I have collected few questions here, Dr. Ali. We'll just probably tackle three of them. Okay, so the first question would be, how does edge computing support the deployment of 5G networks and enhance their capabilities? That's
I
it for
think, yeah, thank you so much for the question. I think I've already
mhm,
answered this question while I was
mhm,
talking about the layers of the edge computing. If you refer to the layers, the slide that covers the layer, you can
mhm,
see that it depends on the protocol that you choose. For some protocols, you have 5G. But based on the other protocols, if you are using, for example, Zigbee, definitely is 2.4. If you are using LTE, is
mhm.
40, and so on. So it depends on the protocol that suitable for your device.
Okay, that's great. And then another one, doctor, would be I believe we have discussed, but this is the question: how can edge computing improve the performance and efficiency of autonomous vehicles?
Definitely, edge computing is a part of autonomous vehicles. It's not something separate. So autonomous vehicles, currently, we use
Mm-hmm.
autonomous vehicles, and
Mm-hmm.
all of them are equipped with the sensors, which I've already explained that in the text.
Uh-huh.
So, for example, you have LiDARs, you have multiple sensors, you have sonar sensors, you have radar sensors. All of them
Mm-hmm.
are features of edge computing. They collect data,
Mm-hmm.
and some of the data locally processed, and the car makes decision. For example, if the car finds an obstacle in front of the car while it's on autopilot,
Mm-hmm.
then it makes decision to stop immediately or reduce the speed while the proximity is closer than threshold to a front car, so it
Mm-hmm.
reduces the speed without interaction of the human. So this is the concept of edge compute.
I see. All right. Thank you so much. And the last one, doctor. Yeah, I still believe we have discussed this, but this is the question. So, what are the environmental impacts of edge computing and how it can contribute to sustainable technology practices?
So
That's the last
definitely,
question, doctor.
it's not directly been discussed, but definitely, while you have less power consumption, this is the first and the most important impact of having a sustainable environment. So you have opportunity to use green energy resources because you need less energy consumption rather than having a cloud which use a high energy and needs high power consumption. So this is very important.
So that's I saw questions here actually being raised up, but definitely because of our time, so probably we'll just get back to you through email. So if you do have any questions, again, please feel free to reach us here at EIT. So as you can see on the chat box, we have our email address. So again, please reach us. We will be happy to, of course, assist you with that one. Okay. So for those who have been asking about the certificate of attendance, here's it. So just kindly scan the QR code as you can see on your screen, and then also the link. So I will be posting in the chat box the link so that you can um, receive your certificate of attendance. And again, Dr. Ali, thank you so much for your time, for sharing this information with us. And of course, well done. Well presented, a very detailed webinar. So again, and also for the attendees today for being with us. Thank you so much, and of course, hope to see you in our future webinars. Have a good one. Thanks, Doctor.
Thank you so much. I appreciate it. Thank you. See you. Bye.
Bye.